Alright, let's sketch the following function with attention to domain range, asymptotes, intercepts, and behavior. And here we have f of x is equal to 1 over x minus 3 minus 1. So this is actually a reciprocal function, right? Specifically, this is the reciprocal of a linear function. You can notice here that on the denominator, we basically have a linear function in the form of y is equal to mx plus b, right? Well, technically it's an expression, right? So it's going to look like mx plus b, and you can notice that x is to a power of 1, right? So it is basically a reciprocal of a linear function, and we're going to call this a linear reciprocal function. Okay, so let's say we wanted to analyze this function. So let's start with the domain and range. So if we're starting with the domain and range here, for the domain, x can belong to the set of all real numbers. However, there is a single restriction that x cannot be equal to, and we can understand that if we have f of 3 here, then 1 over 3 minus 3 minus 1 is going to give us 1 over 0 minus 1, and 1 over 0 doesn't exist, right? So because this doesn't exist, we say x cannot equal 3. Okay, so that's the restriction on the domain. If we're looking at the range here, if we take a look at this function, well, this portion of the function, the 1 over x minus 3, we can notice that this is a fraction, and we know that fractions can only equal 0 when the numerator is equal to 0. However, in this case, for the reciprocal function, the numerator will never become 0 because it's a constant 1, right? So we can notice that this cannot equal 0. So because this fraction, this portion here cannot equal 0, 0 minus 1 doesn't happen. So we can say that y belongs to the set of all real numbers, but y cannot equal negative 1, right? So if you're looking at a reciprocal of a linear function, you can always note that the y-intercept here, the negative 1 here, will be the value of the restriction on the y, right? Now, the next thing we want to do here is we want to look at asymptotes. So if we're looking at asymptotes, the restriction on the domain represents the vertical asymptote. So the vertical asymptote, and we know that asymptotes are basically points that don't actually exist on the graph, but the graph will basically extend towards infinity or a certain value, closer and closer to that point, right? So vertical asymptote is the restriction on the domain. So the vertical asymptote in this case is x is equal to 3. The horizontal asymptote in this case is the restriction on the range, which is basically y is equal to negative 1. So that's what you want to try to understand. And once you have these asymptotes, what you can do here is you can actually graph this on a certain grid, right? So if we're going to graph this, I'm just going to kind of create a sketch here because I want to sketch this function at the end of the day. I'm going to try to sketch this here. Okay, so this is my graph, and I'm going to make the vertical asymptote in red. X is equal to 3. So let's say this is my vertical asymptote here. Okay, so this is my vertical asymptote. X is equal to 3. Right, I'm going to make each of these giant squares go up by 1. And my horizontal asymptote, I'm going to do this in green. My horizontal asymptote is y is equal to negative 1. So this is my horizontal asymptote. Y is equal to negative 1. So these asymptotes act as essentially a boundary or a barrier, and it prevents the graph from crossing these points. Now, the next thing you want to do here is you also want to find the intercepts. So I'm going to take a look at part C here. So I'm looking at my intercepts. You want to look at your x-intercept and your y-intercept. So I'm going to start off by finding my x-intercept. Okay, so we know that the x-intercept exists when the y value is 0. So I'm going to let f of x equal 0. So if I let f of x equal 0, I get 1 over x minus 3 minus 1 is equal to 0. I'm going to move the 1 to the other side. You get 1 over x minus 3 is equal to 1. And what I'm going to do is I'm going to do the reciprocal. You can also cross multiply, it's the same notion. And you basically get x minus 3 is equal to 1. I'm going to move the 3 to the other side. X is equal to 4. So because y is equal to 0 and x is equal to 4, the point here is 4 and 0. So that's my x-intercept. So my x-intercept in this case, let's say it's like somewhere here. Okay, so I'm just going to keep using this grid system. So this is the point 4 and 0. So using my point 4 and 0, I have to use the confines of the asymptote. So if I'm using the confines of the asymptote, what I'm going to do here is I'm going to sketch my graph in orange. And if using the confines of the asymptote, I can notice that this is my grid system. Remember that this is once again a sketch. If you want exact points, you could use some test points, you can plot it in, but we just want to get the idea across. Now we also want to find the y-intercept. So if I want to find my y-intercept here, what I want to do here is I'm going to let x equal 0. If I let x equal 0, I'm going to do f of 0, which is equal to 1 over 0 minus 3 minus 1, which is basically negative 1 over 3 minus 1, which is basically negative 4 over 3, right? Because 1 is basically 3 over 3. So I have the point 0 and negative 4 over 3. That's my y-intercept. Okay, and 0 and negative 4 over 3. This is approximately negative 1.0 and negative 1.333. Right, let's keep going. So let's say that that point here is located, right, it's a slightly lower than 1. So let's say it's somewhere here. Okay, so this is 0 and negative 1.33. Or if we want to use the exact value, we can do 0 and negative 4 over 3. Okay, so and then we can use these asymptotes to act as boundaries. So this is your graph. It's going to follow the asymptote. And we can actually determine what the asymptote really is by looking at the end behavior of the graph, which I'm going to show you in this next step. So the end behavior is what direction does y head when x approaches either positive or negative infinity or the asymptotes? Well, let's say x is approaching, okay, this is negative infinity for x, this is positive infinity for x, this is positive infinity for y, and this is negative infinity for y. So let's say that x approaches negative infinity. Okay, and if you guys do take calculus, you'll also find another way of expressing this, but for the time being we'll just use arrows to represent approaches. So as x approaches negative infinity, as I go this way on the graph, what's going to happen to y here, if you follow the trace in orange, the graph, or the y values actually approach the asymptote y is equal to negative 1, and they get closer and closer. And you can also notice that y approaches negative 1 from below the asymptote. So to show that it's below the asymptote, we usually put a little negative sign. You can also write down below if you want. The other case that you want to look at is this vertical asymptote. Let's say we approach this vertical asymptote. Now you can approach the vertical asymptote from the left side, or you can approach the vertical asymptote from the right side. Now if I'm approaching the vertical asymptote from the left side, you can write this as the vertical asymptote being 3. You can write this as 3 negative. This is approaching it from the left side, or 3 left. And 3 negative just means that it's a value that's really close to 3 that's approaching it from the left side. This could be like 2.99. Approaching it from the right side, we can express this as 3 positive. So a value that is very close to the right of 3 is like 3.001. So as x approaches 3 from the left side, if it's a value like 2.99, it gets closer and closer to 3 in small increments. We can notice that the graph here in orange, it basically will approach negative infinity. Okay. Now as x approaches 3 from the right side, so I'm going this way to 3, you can see that the trace here gets closer and closer to 3, but it'll go all the way to positive infinity. So y actually approaches positive infinity. So these are what we call end behavior, right? You can see that there, and you can see that using the arrows, right? And usually around an asymptote, y will always kind of approach infinity. So if you approach a vertical asymptote, you're going to approach infinity. But as x approaches positive or negative infinity, y will approach a horizontal asymptote. So this is very important to understand. And as x approaches positive infinity, so as I go this way to the right of the x values, you can see that the asymptote of the graph here is going to approach the horizontal asymptote. Y is approaching negative 1, but this time up top from above, right? So we just write negative 1 plus. And yeah, that's our sketch for our reciprocal function. Alright, let's sketch the following function with attention to domain range, asymptotes, intercepts, and end behavior. So here's our function. This is a reciprocal, it's a linear reciprocal function. F of x is equal to negative 2 over 2x minus 8 plus 3. What you can do here is you can simplify it. You can write this as f of x is equal to negative 2 over 2. I'm going to factor out the 2 on the denominator. You get x minus 4 plus 3. And what you could do here is you can cancel out the 2. So technically you can rewrite this as negative 1 over x minus 4 plus 3. It'll give you the same answer if you work with this function or this simplified function. Let's work with the simplified function. Now just by looking at the simplified function, you can notice that the domain of this function, x can belong to a set of all real numbers, but one value that x cannot take on is 4, because if x is equal to 4, then the denominator here would become 0, and that becomes a restriction. So x cannot equal 4. If you look at the range here, right, y can belong to the set of all real numbers, but the one value that y can't take on, and if you take a look at your function here, this portion here, the negative 1 over x minus 4, there's no value of x that can make this 0, right? The only way you can make a fraction 0 is if the numerator is 0. In this case, the numerator can never be 0, so as a result, 0 plus 3 doesn't happen. Y belongs to the set of all real numbers, but y cannot equal 3. So that's something that you want to note. Then the next thing you want to do here is look at asymptotes. Now, we said that the vertical asymptote is the restriction on the domain. We can see that x cannot equal 4, so the vertical asymptote is basically going to occur when x is equal to 4. That means that this point will not exist on the graph, so the graph will not cross x is equal to 4. The horizontal asymptote occurs as a restriction on the range. In this case, the horizontal asymptote is y is equal to 3, and we know that the graph will never cross y when it's equal to 3. Okay, so these are two values that won't exist, and we can use this to kind of sketch your graph out, right? So if I do kind of create a generalized sketch here, and I'm going to make each unit go up by 2, so I'm just going to draw out a grid here. Okay, so I'm just going to go up by 2's. This is like 2, 4, 6, right? This is 0, negative 2, negative 4, negative 6, right? You can kind of create an appropriate scale for your graphs. Okay, so that's my sketched Cartesian plane, and what you want to do here is let's plot our asymptotes. My vertical asymptote I'm going to do in red. So this is my vertical asymptote. Okay, so this is my vertical asymptote. X is equal to 4. My horizontal asymptote is y is equal to 3. I'm going to just do this in blue. So y is equal to 3. Let's say it's the midpoint of 2 and 4. Okay. Technically, you would want to use a ruler for this. So y is equal to 3. Right? Just getting an idea of this. Let's take a look at some of our intercepts. So to find our intercepts, what we have to do here is we need to find our x-intercept. I'm going to let y equal 0, right? So I'm going to let f of x equal 0, and if I let f of x equal 0, you get negative 1 over x minus 4 plus 3 is equal to 0. I'm going to move the 3 to the other side. You get negative 1 over x minus 4 is equal to negative 3. What I'm going to do here is I'm going to do the reciprocal, right? So you get, and the negatives can cancel out if you divide them, right? So you get x minus 4 is equal to 1 over 3. X is equal to 1 over 3 plus 4, and you can imagine here that 4 you can write as 12 over 3. So this is basically 13 over 3. So it's slightly higher than 4, so the x-intercept here is going to be like 4.33. And this keeps going, right? So this is like 4.33. So 13 over 3 is going to be like somewhere here. So this is 13 over 3 and 0. So that's my x-intercept. And then you also want to figure out your y-intercept. Well, if I'm figuring out my y-intercept, I'm just going to let x equals 0, because at the y-axis, x is equal to 0. So I'm doing f of 0 is equal to negative 1, 0 minus 4 plus 3 is 1/4 plus 3, which is 12 over 4, which is 13 over 4. Okay, so in this case, you basically will get 3, 1 over 4. So that's like 3.25. So that's going to be like somewhere slightly higher than this. So this is like 0 and 13 over 4. That's my y-intercept. And using this, you can kind of create your sketch. So if you're creating your sketch, you can use the confines of the vertical and the horizontal asymptote. You can create some test points to make a more refined sketch, right? So we can see that as the graph extends, as it gets closer and closer to the horizontal asymptote, x can approach negative infinity, and you can also create the other sketch here. So you can see that it gets closer and closer to these asymptotes, but it'll never touch, right? Because the points don't exist. Right, so you can kind of see that there. So once again, this is a sketch, guys. You can create you can create a refined sketch if you wanted to do test points, but that's not the purpose of what we're doing here. And what we want to do now is we want to look at some end behaviors just to understand what these asymptotes mean. So if we're taking a look at some end behaviors, I'm just going to do it here, for EV for end behaviors. Right, I'm going to take a look when x approaches negative infinity. So as I'm going this way on the graph, you can see that as x is continuous in the negative direction, y actually gets closer and closer to this horizontal asymptote. You can see that it gets narrower and narrower, and y is going to actually approach 3, but from above. Right? Now, in the other case, as x approaches the vertical asymptote, right, and the vertical asymptote being 4 from the left side, you can see that y actually gets closer and closer. You can see that the graph is going to go closer and closer to infinity. It'll extend all the way to infinity. Okay, and as x approaches 4, this is 4 from the left side, but if it approaches the vertical asymptote from the right side, 4 positive, right, y can actually approach, you can see that it's extending, y actually approaches negative infinity, and as x approaches positive infinity, right, so as x approaches positive infinity, y actually approaches the horizontal asymptote 3 from below. Okay, so this is the end behavior of this reciprocal function. So that's how you sketch out the function and list some of its key characteristics. Alright, let's take a look at a reciprocal quadratic function. So here we have a reciprocal quadratic function. So you can see that the denominator here has a degree of 2, right? And let's assess some of these characteristics that include domain range, asymptotes, intercepts, and we'll also take a look at the end behavior. Okay, so let's start with the domain of this function. So when you're looking at the domain, once again, you're just kind of assessing the denominator. You're trying to look for restrictions. So the denominator here, you notice that x belongs to our real number, but what really makes the denominator 0 and what makes it a restriction is that x cannot equal 3, right? So you can actually notice that here, right, x minus 3 cannot equal 0, so therefore x cannot equal 3 if you move the 3 to the other side, right? So x cannot equal 3, so this is a restriction on the denominator. Let's take a look at the range. And you can notice that this is really the same methodology as when we looked at the linear reciprocal functions. So when you're looking at the range, you can notice that this value here can never equal 0, because the only way to make a fraction 0 is if the numerator is 0. And as a result, you can notice that y belongs to all real numbers, and y cannot equal 0 minus 2 doesn't happen, so y cannot equal negative 2. Okay, so that's also very important to understand, right? Okay, so beyond that, what we need to do now is we need to also assess the asymptote. So we know that the restriction on the domain represents a vertical asymptote, right? So the vertical asymptote is basically x is equal to 3. So this is a value on the graph that the graph won't cross, right? It's a vertical line because it's associated with x, and this is a boundary that x cannot be. And then we know that the horizontal asymptote in this function here, right, is y is equal to negative 2. Okay, so this is the horizontal aspect that the graph won't cross. Okay, so now that we have both of these cases, right, the next thing you want to look at here is the intercepts. And beyond that, after we find the intercepts, we can create a much more refined sketch. So let's take a look at some of the intercepts here. Let's start with the x-intercept. Okay, so let's find the x-intercept. I'm going to let f of x, or y, equals 0. So if I let y equal 0 here, you get 2 over x minus 3 squared minus 2 is equal to 0. I'm going to move the 2 to the other side. You get 2 over x minus 3 squared is equal to plus 2 over 1. What I'm going to do is I'm going to do the reciprocal, and you get x minus 3 squared over 2 is equal to 1/2, right? What I want to do here is I want to isolate for x. I'm going to multiply this by 2, and I'm going to do the same thing to the other side. And here you get x minus 3 squared is equal to 1. And if you want to solve for x, what I'm going to do is I'm going to do the square root. I'm going to do the same thing here, and then the square and the square root cancel out. And remember that the square root of 1 is basically plus minus 1. So this indicates that we're going to have two x-intercepts. So one of our x-intercepts here, x is equal to plus minus plus 3. So one of the x-intercepts is x plus 1 plus 3, which is 4. And the other x-intercept is negative 1 plus 3, which is 2. So you have 4 and 0 and 2 and 0. So those are our two x-intercepts. Now let's find our y-intercept so we can create a much more refined sketch. So the y-intercept here, I'm going to let x equal 0. If I let x equal 0, I'm doing f of 0 here is equal to 2 over 0 minus 3 squared minus 2, which is 2 over negative 3 squared minus 2, which is 2 over 9 minus 2. And you can write the negative 2 here as 2 over 9 minus 18 over 9, which is negative 16 over 9. Okay, so you get negative 16 over 9. This is approximately, it's a little less than negative 2, right? So you can think about this as negative 7 over 9 if you want. And what you can do now is let's create a sketch of this function. Okay, so I'm just I have all my information that I need. I'm just gonna create a grid system out here. Okay, hopefully I have enough space to kind of work with this. Right, so this is like negative 2, negative 4, alright, negative 6, this is 2, this is 4, this is 6. Right, so I'm just going to go up by 2's here. Right, you can create a much more appropriate scale. Okay, so what I'm going to do here is I'm just going to get rid of some of these values. Right, so we kind of did the calculation already. So we have negative 16 over 9 here. Just going to redo that, rewrite it so we can. Okay, so we understand that, and what we want to do here, let's plot these points. So let's first plot our vertical asymptote. So our vertical asymptote, let's just do it in red, x is equal to 3, so it's going to be in the middle here. And what happened there? Okay, so this is my vertical asymptote, x is equal to 3. My horizontal asymptote, and I would advise you guys to use a ruler for this. My horizontal asymptote, let's do it in green. It's going to be y is equal to negative 2, so let's say it's here, right? So horizontal asymptote, y is equal to negative 2, and let's plot our intercept. So one of our intercepts here is 4 and 0, so let's say it's somewhere here. This is 4 and 0. The other intercept is 2 and 0, so let's say it's here, right? And we also have an intercept at negative 16 and 9, so let's say it's like somewhere here. Okay, so this is 0 and negative 16 and 9, and now we can create our sketch. So if we're creating our sketch here, let's do that in yellow. Okay, so you can notice here that one of our graphs will look like this, and the other graph in the adjacent quadrant will look like that. Okay, so you can see that the end behaviors that are close to the asymptote, what I'm going to do is I'm going to try to fix this up a little bit. Close to the asymptote are both going to positive infinity. And this is actually a hallmark feature of reciprocal quadratic functions, right? So let's take a look at our end behaviors. So if we're looking at our end behaviors, this is using a different color, right, using this graph, we're looking at our end behaviors. Right, so if we're looking at end behaviors, first I'm going to assess x is approaching negative infinity. So I'm going to the far left of my Cartesian plane. So you can notice here that y here is approaching the horizontal asymptote, and it's approaching it from up top. As x approaches the vertical asymptote, let's say the vertical asymptote here is 3, right? This is 3 from the left side, this is 3 from the right side. If we approach the vertical asymptote from the left side, y approaches, and you can see that if you follow the trace, y gets closer and closer and extends all the way to positive infinity. As x approaches 3 from the right side, you can notice that y is also approaching positive infinity as well. So as we go this way, y will get higher and higher all the way to positive infinity. And furthermore, as x approaches positive infinity, right, you can see that as we go this way, y actually gets closer and closer to the horizontal asymptote, and it's from the top half as well. So you can notice that as x approaches positive or negative infinity, the horizontal asymptote is being approached at the same direction and as x approaches the vertical asymptote from both directions, you also approach the vertical asymptote from the same direction. So there's just a sense of symmetry associated with these quadratic reciprocal functions, right? So it's almost as if the vertical asymptote creates a line of symmetry, but this is the idea, right? So you have to understand that some of these functions, they'll have different characteristics. It's really important to kind of understand some of these characteristics, and probably the best way to do that is by sketching. All right, let's take a look at another quadratic reciprocal function. All right, and if we actually take a look at this quadratic reciprocal function, if we look at the denominator here, this is a quadratic function, and we can actually, if we test this using the discriminant method, which is b squared minus 4ac, we can actually note that this is going to be a perfect square trinomial. Now, one way we can tell that this is a perfect square trinomial if the discriminant b squared minus 4ac is equal to 0, right? So in order for me to test for this, I'm just going to write down my coefficient and my constant values. So a here is 1, b here is -8, and c here is 16. And I'm getting these values because I'm looking at the standard form of a quadratic, ax squared plus bx plus c, okay? And you can notice here that if I plug this in, you get -8 squared minus 4 times 1 times 16, which is basically 64 minus 64, which is 0. Okay, so this is equal to 0. So because this is equal to 0, this implies that we have a perfect square trinomial. And if you have a perfect square trinomial where a is equal to 1, then you can actually factor it as x plus 1/2 b squared. Okay, so if b is equal to -8, 1/2 b is equal to -4. So technically, I can factor all of this into x minus 4 squared. So I'm going to rewrite this function as f of x is equal to -2 x minus 4 squared. It actually seems a lot less intimidating now, is the minus 1. Okay, so let's take a look at the domain and range of this function, right? So this is the function I'm going to be using now. Let's take a look at the domain and range of this function. So I'm going to start with the domain. So the domain here, x belongs to the set of all real numbers. We can understand that x cannot equal 4 because then you would basically have a restriction on the denominator, and that's not gonna, that value wouldn't exist, right? If we take a look at the range, we can say y belongs to the set of all real numbers, but y here cannot equal -1. And the reason y can't equal -1 is because this portion here cannot equal 0. And the reason this cannot equal 0 is because a fraction can only equal 0 when the numerator is 0. In this case, the numerator is -2. It can never be 0, so 0 minus 1 doesn't happen. So that's why y cannot equal -1. Now, after we find the domain and range, what we're going to do next is we're going to find the restrictions. The asymptotes. And the asymptotes, the vertical asymptote is the restriction on the domain, so the vertical asymptote is x is equal to 4. The horizontal asymptote is the restriction on the range, which is y is equal to -1, so we understand that. The next thing we want to do here is also find our intercepts. So if we want to find our intercepts, I'm going to find my x-intercept and y-intercept. Let me start with my x-intercept first. And to find my x-intercept, I'm going to let y or f of x equal 0. Well, if I let f of x equal 0, we get -2 x minus 4 squared minus 1 is equal to 0. I'm going to move the -1 to the other side. You get -2 x minus 4 squared is equal to 1. What I'm going to do is I'm going to do the reciprocal so I could solve, right, for x. So you get x minus 4 squared over -2 is equal to 1. I'm going to multiply this by -2. Whatever I do to one side, I'm going to do the other side in order to solve for x. So you get x minus 4 squared is equal to -2. I'm going to square root both sides to get rid of the square root. You can actually notice that there is an issue here. Okay, so you can actually notice that, if I square root the -2 here, this is undefined. So this implies that there is no x-intercept, right? So there is no x-intercept, and basically what that's telling us is that this numerator here can always, the denominator here is only positive, right? So you can notice that this value will always be positive. So because this is always negative, right? Negative divided by positive is negative. Negative minus 1, this value will always be negative. So this tells us that f of x will always be less than or equal to 0. Okay, so this is basically the idea, right? Well, sorry, it's f of x is always going to be less than 0. It's always going to be negative. It can't be positive. So f of x will always be less than 0, right? So it's always going to be underneath the x-axis, right? So that as a result, there is no x-intercept. So this is very important to understand. We can attempt to also find our y-intercept. So if I'm finding my y-intercept, I'm going to let x equal 0, excuse me. So if I do f of 0 here, we get negative 2 over 0 minus 4 squared minus 1, which is negative 2 over 16 minus 1, right, which is basically negative 18 over 16. Okay, so negative 18 over 16 you can write as negative 1, 2 over 16, or 1 over 8. Okay, so that's our values. So our y-intercept does exist. We have 0 and negative 1 over 1 over 8. Okay, and what we want to do now is let's sketch our function out. Okay, so let's plot our vertical asymptote, our horizontal asymptote, and let's get an idea of what this graph will look like, and then we're going to take a look at end behavior. So we notice that, right, this graph should not cross the x-axis, and that y should always perpetually be less than 0. Okay, so let's take a look at, let's say we go by 2's here. Okay, so I'm just going to kind of create my Cartesian plane. Okay, so we also can understand here that our vertical asymptote is 4. So I'm just going to draw my vertical asymptote in red. So x is equal to 4. Let's say it's like here. This is my vertical asymptote. X is equal to 4. And my horizontal asymptote is y is equal to negative 1. Let's do that in blue. Right, so if it's negative 1, it's going to be somewhere here. Right, and you kind of want to use a ruler for this, right? I should be using a ruler, but I'm just kind of showing you guys as quick as possible just the procedure so you guys can learn it. And in this case, we want to find the intercepts, right? Well, we want to plot the intercepts. There's only the y-intercept, so if I plot the intercept, we have negative 1 over 8. So it's a slightly slightly below. We have 0 and negative 9 over 8. Okay, and using this notion, we can just kind of create a sketch here, right? So we can notice here that the graph is going to follow the confines of the asymptotes as shown. Once again, it's a sketch, right? If you want a more fine sketch, you would basically use a series of points, right? And because the graph doesn't cross the x-intercept, we can understand that the other graph here should do the same thing. So it should kind of do that, right? And so the graph here will be below this horizontal asymptote. So let's take a look at our end behaviors. See the different color here. Let's take a look at our end behaviors. Right, so to assess our end behaviors, I'm going to say x approaches negative infinity. So as x approaches negative infinity, you can see that y gets closer and closer to the horizontal asymptote from below. Y approaches negative 1 from below. As x approaches, the next step here is let's approach the vertical asymptote 4 from the left side, and we'll also approach the vertical asymptote 4 from the right side. So as x approaches 4 from the left side, y actually gets closer and closer to, if you follow the trace, it gets closer and closer to negative infinity. Okay, as x approaches 4 from the right side as we go this way, right, y also gets closer and closer to negative infinity, because you can see that the trace gets elongated in a downward y direction. And as x approaches positive infinity as we go this way, right, y actually gets closer and closer to negative 1 from below. Right, so there is a sense of symmetry, right, in terms of the approach to the horizontal asymptote and the approach around the vertical asymptote. So that's one of the hallmark features of these quadratic reciprocal functions, right? So it's really interesting to understand this, and this is basically, you can kind of glean a lot of these characteristics by sketching the function. All right, let's take a look at another variation of a quadratic reciprocal function. Okay, so we have f of x is equal to 1 over x squared minus 4x minus 12 minus 2. And actually, if we take a look at the denominator here, we can actually factor this. And you can actually see here, if we do the factoring, you can, two numbers that add up to -4 that multiply -12, you can write this as -6x plus 2x minus 12. And if you factor in x, you get x minus 6 plus 2x minus 6. You get x plus 2 times x minus 6. Okay, so this is our factored format of our function f of x. And the idea here is now we can actually notice that we have two restriction values of x on our domain. So that's what I'm going to take a look at in a second. So I'm just going to rewrite my expression in factored form. So you have 1 over x plus 2 times x minus 6 minus 2. Okay. So let's start with the domain. So starting with our domain x belongs to all real numbers. But here x cannot equal -2 or +6. Both of these values would make sure that the denominator here would be 0, right? Like f of -2 here would give you 1 over 0 minus 2, and this is undefined, right? Doesn't exist. And f of 6 here would give you 1 over 0 minus 2, and this also doesn't exist. Okay, so these are two restrictions on x. So you can notice how this is different from some of the previous examples we looked at. Let's take a look at the range here. The range is still going to be the same thing. So if we take a look at our fraction here, this portion here cannot equal 0 because of the fact that you can only make a fraction 0 if the numerator is 0. So 0 minus 2 doesn't happen. So y belongs to the set of all real numbers, but y cannot equal -2. Okay? So now that we have our domain and range, what we want to do next is we want to look at our asymptotes. So our vertical asymptote is the restriction on the domain, so x can be equal to -2 and 6, and our horizontal asymptote is the restriction on the range. In this case, y is equal to -2. Okay, so we have our asymptotes. What I want to do now is I'm just going to create a generalized sketch with the asymptotes. So I'm just going to do that here. Alright, so here's our Cartesian plane, and what we want to do now is let's plot our vertical and horizontal asymptotes on this grid. So on our vertical asymptote here is -2, so I'm just going to do the vertical asymptotes in red. Okay, so it's -2, so this is one of our vertical asymptotes. The other vertical asymptote here is 6. So this value here. And we also have a horizontal asymptote at y is equal to -2. Okay, so let's do the horizontal asymptote in blue. So this is the horizontal asymptote in blue. So the horizontal asymptote, y is equal to -2. The vertical asymptote is basically x is equal to -2, and vertical asymptote x is equal to 6. Okay, so now that we have those 2 points, what we can do next is we can find our intercepts, right? So if we want to figure out our intercepts, I'm going to start by finding my x-intercept. So I'll just use yellow here. Okay, so let's solve for my x-intercept. If I want to solve for my x-intercept, I'm going to let f of x equal 0. So we get 1 over x plus 2 times x minus 6. Minus 2 is equal to 0. I'm going to move the 2 to the other side. So you get 1 over x plus 2 times x minus 6 is equal to +2. Now let's do the reciprocal here. So we do the reciprocal. We get x plus 2 times x minus 6 is equal to 1/2, right? And what you could do at this point is you could expand this back to its original format, right? So we're going to do x squared minus 4x minus 12, and move the 1/2 to the other side. Minus 1/2 is equal to 0. Then you get x squared minus 4x minus, you can write this as 12.5 is equal to 0. So you can understand that because we've written our quadratic equation as ax squared plus bx plus c is equal to 0, you can actually solve for this using the quadratic formula. Okay, so recall that the quadratic formula, x is equal to -b plus minus b squared minus 4ac over 2a. Okay, so I'm just going to kind of plug these values in and just kind of openly solve for this. I'm pretty sure all of you know how to do this, right? So you have negative 4 plus minus b squared, which is negative 4 squared, minus 4 times 1 times, so a is 1, and then c here is negative 12.5, okay? And this is over 2 times 1. So if I plug this in, x is equal to, so if you crunch this out, x is equal to either 6.062 approximately, or approximately negative 2.062. Okay, so I'm just going to use these values, right? And these are just rounded values. So 6.062, let's say it's like somewhere here. So this is one of our x-intercepts, and the other intercept here is negative 2.062. So it's going to be to the left of the vertical asymptote, right? So we'll call this 6.062 and 0, and negative 2.062 and 0. Okay, so we have those points. And then what you want to do is create your sketch, right? So for your generating our sketch, we want to use the confines of the asymptotes. So if I'm creating the confines of the asymptotes, I'm going to do that this way. Okay, so this is one of our sketches of our graph. The other sketch of the graph is going to look like this, right? And we can also figure out the y-intercept of our function, right? The y-intercept will be a lot easier to find. So if we are trying to find our y-intercept, what we can do here is I'm going to let x equal 0. So if I let x equal 0, I'm going to do f of 0 is equal to, and I can use the original function, so if I plug in 0 for x, you get 1 over negative 12 minus 2, which is negative 1 over 12 minus 24 over 12, which is negative 25 over 12. Okay, so f of 0 is negative 25 over 12. So this is going to look like, it's a little bit more, a little bit less than negative 2. So this is like 0 and negative 25 over 12. Okay, it looks like that. And this is another point out. Basically, there is going to be, in these types of functions where you have two vertical asymptotes, there's going to be a parabola that's going to be located in this middle quadrant that is created by the asymptotes intersecting each other, right? So the way we can figure out the parabola has a vertex, and the x value of the vertex, and this is something that you want to remember, the x value of the vertex is the midpoint of the vertical asymptote. So you have vertical asymptote 1 plus vertical asymptote 2 divided by 2. So the first vertical asymptote here is negative 2. Second vertical asymptote is 6, and you divide this by 2, so you basically get 4 over 2, which is 2. So the x value of the vertex is 2. Once you have the x value of the vertex, you want to find the y value of the vertex. I'm going to do f of 2 and plug it into my original function. So if I plug in f of 2 into my original function, I'll just use the factored form. I'm doing 1 over 2 plus, I think our function here was 2 plus 2, 2 minus 6 minus 2, okay, which is basically 1 over 4 times negative 4, it's negative 16, minus 2 is basically 32 over 16, and this is basically negative 33 over 16. Okay, so f of 2 is negative 33 over 16, so the point here is 2 and negative 33 over 16. Okay, so this is going to tell us that, right, the x value of the vertex is here, and negative 33 over 16 is slightly above this value, so it's going to base, well, sorry, it's slightly below this value. So this is the vertex. Okay, so technically if we do a sketch here, I'll use a different color. Oh, let's use green here. Okay, so if we do a sketch here, this is what the parabola will look like. Okay, so it is somewhat narrow. We are kind of just generating a sketch. This is what the parabola will look like. So this point here is the vertex, and the vertex is 2 and negative 33 over 16. Okay, now we basically have an axis of symmetry that gets generated. Maybe we should use a different color. Let's use purple here. We get an axis of symmetry that gets generated at x is equal to 2. Okay, and this axis of symmetry actually creates two mirror images, right, that crosses the x value of the vertex. So the axis of symmetry, it actually creates a mirror image of the entire quadratic reciprocal function. So this is very interesting to kind of note. It actually creates a mirror image of the two halves of the graph. And you can notice that the sketch of this function is quite complex, right? And the last thing we can do here is we can assess the end behavior. Now the end behavior here is quite complex because there's going to be, we have to look at both asymptotes, right? Because of the fact that we have to look at the left and right side of the asymptotes. So let's take a look at the end behavior. Right, so these questions do take a little bit of time. Let's start by x approaching negative infinity. What happens to the function? Well, if we go this way on negative infinity, then we can notice that y actually approaches the horizontal asymptote, right? Y actually approaches negative 2 from above, right? So y approaches negative 2 from above. You can actually notice the same thing occurring as x approaches positive infinity. Y also approaches negative 2 from above, right? So if we're saying above, we should put a plus sign here. Okay, so this is negative 2 from above, and then what you want to do here is let's approach the vertical asymptote. I'm going to use a different color. You can approach the vertical asymptote from the left side of negative 2 and the right side of negative 2. So if I approach the vertical asymptote from the left side of negative 2, y actually approaches negative infinity. Right, and if I approach the vertical asymptote, positive infinity, we're looking at this portion. So it's positive infinity, right? Because we're basically, as we go this way, the graph goes upwards. And as we approach the vertical asymptote from the right side of negative 2, y approaches negative infinity because we're going this way, and then this graph, this trace is going downwards, right? So you're looking at the trace in green this time. We can also look at the other asymptote, 6, from the left side and the right side. So as x approaches 6 from the left side, y is actually going closer and closer to negative infinity. So y approaches negative infinity, and as x approaches 6 from the right side, right, y will basically approach positive infinity. That's what you see there. Okay, so you can notice that the end behavior is a lot more complex, and you actually have to test 6 different values. So this is the sketch of a quadratic reciprocal function with two vertical asymptotes. Okay, so it's very interesting. It's